Hello and welcome to the Physics 2 first lecture here in Chapter 17. We're going to do a short summary here of sections 17.1 through 17.3, and then I'm going to go through each one of those sections individually so you have an idea as to what we're talking about here when it comes to electricity, which is what we're getting into next. So let's talk about the summary here that we have for these first three sections. What we're going to be talking about here are conductors and insulators. So the fundamental entity in electrostatics is going to be electric charge. It's either going to be labeled as positive or negative. Like charges repel each other, unlike charges attract, which is kind of what you see going on in this particular diagram. You've got like charges, like positive charges here. If you have a rod that is suspended but is able to move back and forth, if you take another positively charged rod and bring it towards it, it's going to move the other direction because like charges don't like being close to each other. Same thing is going to happen here if you have two rods together that are negatively charged. This one is going to push this one away. If, however, you were to take objects that are oppositely charged, like a piece of fur or a piece of silk, and you've got rods here that have the opposite charge of what's being held on this, they're going to pull on each other. So like is going to repel like, and unlike charges are going to attract, opposites attract. That's how you can remember that. Conductors are materials that permit electric charge to move within them. Insulators permit charge to move much less readily. Now, it's not as if the fact that in conductors electric charge movement is considered good, or insulators are considered to be bad. It's just that's the way it is. We need to be able to take advantage of both situations in order to be able to produce something of human value. Most metals are good conductors and most non-metals are insulators. All ordinary matter is made of atoms. They consist of protons, neutrons, as well as electrons. The protons and neutrons are going to be in the center of the atom, the electrons surrounding the nucleus at a distance that are far greater, and we'll get into that a little bit. They rotate in certain orbitals. Electrical interactions are chiefly responsible for the structure of atoms, molecules, and solids. Electrical charge is conserved. It can be transferred between objects, but isolated charges cannot be created or destroyed. Electric charge is quantized. Every amount of observable charge is an integer multiple of the charge of an electron or proton. So in other words, you can't divide it any more evenly than the charge that an electron or a proton carries, and you will see multiples of that, but you will not see fractions of that. That's just kind of the way that works. Okay, so let's talk about electric charge here. This goes back even as early as 600 BC, when you could take amber and you could rub it with some wool. Greeks would actually see that the amber could attract other objects, and I'm sure that was kind of weird, and they really didn't have any sort of explanation that I'm aware of for that, but it did have an effect. And we say that the amber has acquired a net negative charge, or has become charged. And then the word electric is derived from the Greek word electron, which meant amber. So you can see the connection there. So when you scuff your shoes along a nylon carpet, you become electrically charged, and you can charge a comb by passing it through dry hair. So plastic rods and fur are particularly good for demonstrating electric charge interactions. So let's take two plastic rods and let's rub them with a piece of fur. So that's what's going on. And then we're going to find that the rods are going to repel each other. I mean, they've gone through the same type of interaction here, so it's not surprising that they would develop the same charge. And now we know that like charges repel each other. So if you rub the glass rods with silk, the glass rods also become charged and repel each other. What you're going to find is that in different situations, the charge is going to be different, but it's going to be the same type of charge on each rod. Now, a charged plastic rod is going to attract a charged glass rod. And then furthermore, the plastic rod and the fur are going to attract each other, and the glass rod and the silk are going to attract each other. So if you were to take just plain plastic rods and hold them up to each other, you're not going to see any sort of electrical interaction. Just not going to happen. So you take it and you rub those rods with fur, you're going to see that they repel. If you take plain glass rods, they're electrically neutral. They're not going to interact. But you take it, you rub it with silk, and you end up with positive charges on each. Again, it's going to repel. But if you were to take those rods and you were to put them close together, you would find that this that was rubbed with silk, and then this that was rubbed with the fur, this plastic rod and this glass rod, the plastic being negatively charged, the glass being positive, they're going to attract each other. And then if you take the glass rod and the silk, or the plastic rod and the fur, and hold them close to each other, they're going to attract. This is an interesting little story here to read. If you went to, this person here was taking a vacation at Sequoia National Park, and her hair was standing up on end. As it turns out, she and the friend that she was with ended up leaving the overlook right before it was hit by lightning. What happens before a lightning strike is that strong charges build up on the ground, and what you're seeing here are the effects of that the hair strands are being attracted upwards. Because like charges repel, all of your hairs tend to get as far away from each other as they can, but the key thing for you is to get as far away from that spot as possible. So let's see, the physical basis of electric charge. When all is said and done, we can't really tell you what electric charge is. I mean, we can quantify it, and we can discuss it and what the effects of are, but we don't really know exactly what it is. But we've figured out enough about it to be able to model the activity. So the interactions responsible for the structure and properties of atoms and molecules and all ordinary matter are primarily electrical interactions between electrically charged particles. So as we discussed before, you've got the electrons out here in an atom, and inside here in the nucleus, you've got protons as well as neutrons. And this nucleus is going to contain over 99.9% of the atom's mass. And that nucleus is going to be 10 to the minus 15th meters. That's pretty small. What you're going to find is that the electrons are going to circle out here, and they're going to circle at a distance of about 10 to the minus 10 meters. So if an atom were a few miles across, if we were to scale this up, then you're going to find that the nucleus is going to be the size of a tennis ball. So you've got a tennis ball, and then you've got the electrons, which you're going to encounter several miles out. So, and you can see the mass units for proton, neutron, as well as the electron right here. These are the values that have been the most recently measured down to these significant digits, which are, measurements at that point are a little difficult. So the negative charge of the electron has exactly the same magnitude as the positive charge of the proton, which is kind of interesting. In a neutral atom, the number of electrons equals the number of protons, and the electric charge is exactly 0. The number of protons or electrons in neutral atoms of any element is called the atomic number. So you can see here for neutral lithium, you've got 3 protons, 3 electrons. As it happens, 4 neutrons. This number of neutrons can vary, but if they're electrically neutral, then the protons and the neutrons numbers should be the same. If it were to become a positive ion, that means that one of the electrons has been stripped out. And that means that you've got a positive charge, or positive 1 charge here on this. If you've got a negative lithium ion, that means somewhere you've picked up another electron. And as you picked up that electron, it means you've got 1 more than the number of protons. So an ion is an atom that has lost or gained 1 or more electrons. If 1 or more electrons are removed, the remaining positive charged structure is called a positive ion. Negative ion is an atom that has gained 1 or more electrons. And this gaining or losing of electrons is called ionization. So ordinarily, when an ion is formed, the structure of the nucleus is unchanged. In a solid object, such as a carpet or a copper wire, the nuclei of the atoms are not free to move about. The net charge is due to an excess or a deficit of electrons. In a liquid or gas, a negative electric charge may be due to the movement of those ions. So thus, a positively charged region in a fluid could represent an excess of positive ions or a deficit of negative ions, or both. So that's a description of section 17.1. In the next video, I'll discuss 17.2 and 17.3.